hot topic in ITF, so we really wanted to get this discussed here in ISOC as well, and we know that there are a lot of routing experts sitting here. So Adrian, you know quite well by now. He spoke yesterday. I met Adrian at, remember IP Switch, where ages ago, where I have never been to ITF before that. I was just a developer. We went for a demo, and just by talking with Adrian, I said, Adrian hated all the ideas that I have, but I was like, let me prove him wrong, and which is true. Got my RFC published, though he hated it. Rough consensus sometimes, but he has been really inspiring in a lot of ways. His reviews are one of the best reviews that I've ever seen in ITF. You know, when your document gets reviewed by him, it's like, you know, I don't want to say it more. Shraddha, again, I've known her for a long time. We were colleagues in the past life. We have wartime stories from Beijing and other places. She is a true expert in routing domain. She has been involved with IGP, LDP, now segment routing, and it's like, you know, it's a pleasure to work and collaborate with her. So I would invite both of them to start talking.
She'll answer all the questions, and I'll say all the stupid things. And I think the first thing, before even telling you an agenda, is to say there are lots of data centers already deployed. People have deployed data centers for a very long time. It's almost true that every data center that has been deployed is different. There's no cookie cutter for data centers, and although one operator may try to make their data centers look similar, they inevitably evolve and change, and different ideas come along. So the protocol work that Shraddha will talk about is evolving and hopefully will be standard. The topology work that I will talk about is very high-level, hand-waving, aspirational. So we're roughly splitting it with me talking about background and Shraddha doing the real work. A history. I think originally data centers were Ethernet bridge networks, a dynamic tree topology, so spanning tree, and as long ago as roughly 10 years ago, we started to peak out on what spanning tree could do, and data centers just kept growing. Convergence became a problem, performance issues, and so on. So some specifics there. The Ethernet VLAN has a theoretical capacity of 4,096 tenants. Now you can double encapsulate, but for a simple implementation, that's a bit limiting. And spanning tree has obvious limits that we all know in terms of scaling and convergence. And actually also load balancing. There's a tendency in spanning tree for all the traffic to go the same way. And lastly, and this was mentioned a bit earlier, mobility becomes entertaining, and so Ali was talking about how EVPN handles that, but it has been a problem in the past. So the objectives, what we're trying to do with a data center, dictates the topology, the way you actually build out your data center. Essentially, there are very, very large clusters of servers, each hosting very many virtual machines, and a high volume of traffic going in and out of the data center. So the gateways are heavily loaded, and some data centers, of course, that are often replicating their entire contents to another data center. That's just a huge blob of data going. But there's also high volumes of traffic within the data center. Data centers need to be able to grow out. You don't make a data center and leave it like that forever. You probably start small and keep adding. You want to do that as a bulk addition. You can't go and add one server today and then another server. You essentially build a whole corridor of racks and plug them in. And this all leads to some common approaches to the DC topology. They're highly connected. You want no server to be more than a few hops away from a gateway, and you want no server to be more than a few hops away from another server, for any other server. You want redundant paths so that there's no single failure in the network will partition the data center. And you want this modular architecture so you can add huge blobs without having to rewire everything else. Way back in 1938, so it's a long time ago, Edson Irwin invented something which is now called a clos network. And he invented it as a sort of logical topology, and it was picked up in 1952 as a way of wiring together telephone switches. Telephone switches had a very limited number of ports and capability, and they wanted to build a bigger switch with more ports, and they came up with this cunning way of wiring the switches together that made a composite switch. In the data center, we build these using IP switches. And we've got two figures here. The top one, slightly more simple, shows some servers at the bottom connected up to what are called leaf nodes because they're the bottom switches in the tree. And it's a very simple three-stage network. The spine is at the top, and the spine is kind of the interconnecting switches and would also provide the gateway outwards. You can see there that each server is exactly 3 hops away from the other servers. And there's, apart from on those last links, there's a redundant path. The scaling on that gets a little bit exciting. As you add more and more servers and leafs, the poor old spines are getting a bit confused. What we do to break that up is add another layer, and this extra layer is called the spine attachment layer, and then we cluster so that we don't have the full every leaf is connected to every spine, but we cluster them into what are called pods. And just, I guess because we've been reading too many comic books, instead of calling these spine routers, we call them super spine. Switch fabric is kind of the old term. We now try to make this an IP switch fabric, or for short, an IP fabric. And this is just a set of IP forwarding nodes, usually using commodity silicon, typically but not always lacking support for MPLS, so they are effectively IP switches. They're arranged into a clos network like one of those figures. There's lots of ECMP, because if you've got redundant paths, you should actually distribute the balance of traffic. The top of rack nodes, the TORs, are given, so that's the top of the pile of servers, are given typically a /24. Sorry, I'm talking IPv4 language, but this is, well, actually, of course, it could be a /24 in IPv6. I didn't, yeah. And this provides a summary of all the tunnel endpoints assigned to that top of rack, and that summary is what's advertised outside the fabric. The fabric is largely static. You may get failures, of course, but you're not often unplugging and plugging things in. So the tunnel endpoints do not move within the fabric. And so the topology is static. Now, if a VM moves, it's moving to another /24. And this means that essentially the routing advertisements are just reduced to failure and repair of links and nodes, and if a top of rack fails, then the whole /24 is withdrawn. Configuration becomes really important, but it's typically automated. And it needs to be automated because it's such a large network, but automation is not so hard because the topology is pretty predictable, and largely speaking, what you've deployed is consistent technology. So it starts with the IP fabric topology and a naming space for the nodes, and then a playbook. And a playbook is just a template that says, when I'm deploying this type of box or this protocol, I do these things. So it's a formulaic sort of cookie cutter approach to configuration. And if you take a diagram of the topology, you just assign addresses as you work through it. There's nothing clever that needs to be done. The nodes go and retrieve their own individual copy of the playbook from the provisioning system. They say, this is my name in the naming space, give me my configuration. And getting that configuration either requires you to have a second backup control plane, which would, I think, be unlikely. So it needs you to provision the network top to bottom so that the lower nodes in the system can get their playbook only when the previous ones have been configured. The nodes are responsible for initiating the links, and they use LLDP or CDP to make sure everything's up, and then establish the protocols. It is necessary that the provisioning systems handle multiple vendors, clearly, and there are a whole host of sort of script-based provisioning tools out there. There are companies that are making their living from producing these playbook systems. And I think this is my last slide. I wanted to distinguish between overlay and underlay routing in the data center. The underlay routing is within the IP fabric. It's how do you get from a TOR to a TOR, or a gateway to a TOR, or a TOR to a gateway. Okay, TOR top of rack, the pile of servers. The overlay routing is across the IP fabric and is about VM to VM routing, or VM out into the big wide world, or back inwards. And this is a layering of routing, just as we are familiar with in other layered networks, but it's important to step back from the data center and recognize that there are these two layers. And this then, I think, is Shredder.
I think I have this. Okay. Thank you. Thanks, Adrian. Let me just recap on the routing problems in the data center. So these are the most popular data center routing that we have so far. So L2 technologies, IGP, and BGP. So L2 technology, we saw what were the problems with Ethernet bridging, scale issues with VLAN tags, slow convergence of spanning tree protocol, and MAC learning. This is basically the absence of underlay and overlay routing. So basically your MAC has to propagate through your entire underlay, and then that's how the routing works in L2, which is not very scalable. The endpoint mobility problem, and we saw how EVPN solves it, so that was absent in L2 technology, which resulted in very slow conversions in L2 networks. And of course, native ECMP is not supported in spanning tree protocol. So those were the problems in L2 technology. So slowly people moved to L3, which started using IGPs. So we still see some DCs which are still running IGP. They run on, at least I have seen some OSPF, NSSA areas inside data centers medium scale data centers who still run on OSPF. So the problems in IGP when it becomes very huge, when the data center network becomes very huge, is the flooding in regular topologies. So we saw the data center topologies in Adrian's slide. It's very regular. So the leaves are connected to the spines, and the spines connected to the super spines. So what happens in IGPs is IGP is a flooding protocol. So something goes wrong, all your neighbors will tell you that something went wrong there. It's the same information everybody is telling you, but then you have to process each one of them, tell them you got that message, and then tell each one of them that you got the message that you told, and that takes time. Processing the redundant information over and over again, that slows down the protocol a little bit. And IGP has also this refresh, database refresh mechanisms, because it runs on, it doesn't run on reliable transport, so you have to keep refreshing your database. That also consumes, you keep sending your database, and then you keep expecting ACKs, and then your router is not able to process it, and then it doesn't reply back with the ACK, and then again you have to retransmit, and that's another problem that's regularly seen with IGPs inside DCs. So we have, so all this led to BGP, right? So BGP, today there are many data centers which have BGP inside the data centers as the routing protocol. So we do see some issues with BGP, which are, the main issues are that it's configuration heavy, and then the slow convergence of BGP. Let's see more in detail in the next slide. So this is one of the widely deployed technologies inside data centers today, which is BGP. So BGP is behaving like IGP. So you have hop by hop eBGP configured on your routers inside the data center. Why is this BGP attractive inside the data centers? It's because it's a reliable protocol. It works on TCP, and so you don't have this the database refresh kind of problems with BGP. So you use TCP, so you know that you've sent a message, it has reached. So you don't have to keep refreshing and expecting ACKs from your protocol. So that's the advantage that BGP brings in. And if you see, you have to do some configuration, but you could do it with minimum configuration as shown in this picture, where you assign, every node is a different AS, but then you could optimize it with, the way it is done here with doing the AS numbering on the spines in the leaves. So you could also do lightweight or minimal traffic engineering. This is basically done using usual BGP policy machine. So you can configure, these kind of prefixes. I don't want to use this path, and then have the traffic engineering. Among your ECMP paths, you could select for certain destinations, you could select only certain paths among your ECMP paths. So that's how the BGP inside the data centers. This is pretty much, there's an RFC which is published in RTGWG, and this is quite popular as a data center routing protocol. So as we saw before, BGP is good, but it does have problems. One of the major problems is slow convergence. Why is it slow? Because BGP is hop by hop, right? So something goes wrong somewhere in your network, you have to tell your neighbor, and that guy has to tell your next neighbor, and that's how it reaches throughout the network, which is very, very slow compared to flooding protocols. But then you have other issues with flooding. So we need a mechanism which can solve this problem. And also with BGP, right, you have hundreds and thousands of prefixes that are attached to your TARs. You have to advertise all those prefixes, and then you have, if something goes wrong, you have to advertise, or you have to withdraw all those routes, or you have to, re-advertise those routes through BGP, which is not the case in IGPs, right? So IGPs, what we do is we just advertise the connectivity to your nodes, and the prefixes that attach to that nodes will get calculated automatically when you do SPF. That advantage is not there in BGP. So those are the two problems with BGP inside the data center. So we have a problem to solve. So we have multiple solutions. So let's see what are those solutions, right? So this is Rift. Rift is the brand new protocol. This is routing in fat trees. So this protocol, it brings in a little bit of link state, a little bit of distance vector, combines them, and then makes it a new protocol. So it's distance vector downstream and then link state upstream. So if we go back to the picture, right, this picture, so from top, from spine to the leaf, it is southbound, which is distance vector, whereas from the leaves to the spine, it is link state. So what do I mean by that, right? So when these nodes advertise their topology, they will advertise the whole topology, like what's the node, what are their links, and they send it to the next level. So the next level, what it does is when it is sending northbound, it floods the information that the lower layer has sent it. And it will include its own information as well and flood it up northwards. Whereas, let's say from this side of the from this side of the network, when the information comes here, right, and then when it's going down, it's percolating down, it only advertises the default routes. So it does not advertise the entire, the nodes and links corresponding to this side of the network. So from here, from the spine, when it's percolating down, it advertises default routes, and it advertises itself like its own node and link information, but it does not percolate down the node and link information of these guys. So that's a lot of reduction in flooding. So you are constraining your flooding information. So that's how you achieve reduction in flooding in this protocol. So it also has automatic link discovery like any other link state protocol. You can automatically discover your neighbors. And it also has a provision to figure out what level you are in. So if you have to configure minimum information, like few nodes in which level they are, like level 0, level 1 or level 2, and then the other nodes will figure out what level they are in based on how they are forming the adjacency. So we also have minimal amount of route information on the leaf or torus, because you saw that from top to down it's only percolating the default routes. That means you have on the leaves you have minimum amount of routing information. Go back to the picture, right? So for these routes, for the prefixes that are attached to these routers, the routing on these routers will happen based on default routing. So you won't see the, let's say prefixes P1, P2, P3 is attached to these set of routers. On these routers, you will only see you won't see the route P1, P2, P3 on these nodes. You will just see a default route. That's a lot of reduction in the routing information on the TORs. So it natively supports ECMP, which is an additional advantage compared to BGP. That's because BGP needs additional paths like add path, multipath, and those to be able to support ECMP, whereas this protocol comes up with native ECMP support. You could also do traffic engineering on all the links, and it supports fastest convergence and automatic disaggregation. So what do we mean by that, right? So what do we mean by the automatic disaggregation? So let's say a certain link on this side of the, so let's say the certain link here fails, right? This link is broken. Then if these guys are doing default routing, they won't know, that information won't percolate down, right? So they will be thinking that, if I can, there will be a default route that this guy will be sending, because he can still reach the other routers, right? So he'll still be sending a default route down. But then these guys who have to reach this one, they cannot use this guy. This information has to somehow go down, otherwise you will have black holing because of the default routing. So this protocol supports automatic disaggregation. What is disaggregation? So instead of the default routing, you split up your routing range. When you when you see that there is a there is a problem here, and then to reach this guy you don't have a route, you automatically disaggregate, and then you send, instead of sending a 000/0, you send, disaggregate and send, make it into 2 ranges, and then send it down such that this guy does not cover that wherever he has lost the reachability. So this happens automatically, no configuration, no additional configuration required, or no manual intervention required. So that's another advantage of Rift. So how much time do we have? Can I go more in detail? Yeah, let's cover other things, and if we have time we can come back to this. So there is, for Rift, we have a working group for Rift, and then so a lot of work going on, a lot of interest in this new protocol. So we have other mechanisms as well, which is being discussed in IETF. The one is flooding reduction in IGPs. There are multiple proposals for how to reduce flooding in IGPs, and there is another which is LSVR, which uses BGP, and then BGP does SPF to solve the problems that are there in the BGP only data centers. So let's quickly go through this flooding reduction in IGPs. So this flooding reduction in IGPs, it always existed. If you can remember the mesh groups in ISIS and a similar variant in OSPF, it existed. But the configuration was manual, it was not really manageable. So the new drafts, there are multiple proposals in IETF. One is this draft Lee dynamic flooding in ISIS, and another draft CC ISIS flooding reduction, and there's one more draft Shu ISIS flooding reduction in MSDC. Let me quickly cover what these ideas are about, right? So draft Lee talks about in an IGP you choose a flooding topology, right? I mean, you come up with a flooding topology. How do you come up with this flooding topology is, local to the box. So the box decides how that flooding topology is computed. So this is a problem, for you guys to think about. How do we come up with a flooding topology which is very optimal and it works in all kind of topologies. And then it chooses a leader in the topology and uses DR, BDR kind of. We all know in IGPs we have this DR, BDR for LANs. It uses kind of similar technology, similar thing, and then uses a tiebreaker for selecting DR and BDR, and that guy will flood the information. That guy will advertise the flooding topology, and then flooding topology will decide who will flood to whom. So this node will flood to this guy, this node will flood to this guy. That's what that's what this draft is all about. So the draft CC ISIS flooding reduction is very, very similar. Only the difference is, how do you, in the protocol, how do you advertise what's the flooding topology, and that's the only difference in these two drafts. And there is another interesting draft. So the last one, draft Shu ISIS flooding reduction in MSDC. This mainly talks about management ports and then flood over those management ports. Those management ports are connected, on a LAN, and then you are using DR-BDR kind of flooding optimizations to flood on inside the DCs, and then your actual traffic forwarding will happen on your other P2P links, but your the topology flooding, the topology flooding is completely blocked on those links where traffic is forwarded. It only happens on the management ports. So that's another idea. So we have this LSVR. This is another working group, and then this is trying to solve the problem in BGP itself. So we have the problem of slow convergence. We have the problem of additional configurations, and we have the problem of black holing in BGP, as we saw in BGP inside data centers. And this is trying to solve this is trying to solve that using. They have a new NLRI which is very similar to BGP LS and LRI, so it advertises nodes and links, and then BGP itself natively computes the SPF using that topology information, and then instead of using BGP best path selection, it uses the computed information to program the routes. So there is a lot of interest in this one as well, and there is a separate working group working on this for standardization. So basically, what I want to summarize is there are a lot of new mechanisms being proposed to solve in DCs. As I'm talking about all these techniques, I think I guess all of you would have chosen, your favorite. You think, oh, I think this is going to work. We really don't know which one is going to work, and I'm pretty sure everyone has chosen their own, and all are different. Different mechanisms that, you guys think that that's going to. So at this stage, it's still not very clear which one is going to sustain. So I want to leave with that thought, and if that gives you some, gets your brain cells tickling, and then that's what is the objective of this talk.
Okay. So I am Annapurni. So I have a question. Like we say, as part of the data center requirements, we want data center want to avoid like Cisco's and Junipers because you are really expensive, right? So we come up with something which is already available in the market. So if you see, like that's why if you see in the large data center, we go for eBGP, correct? And if you see the configurations is more or less similar on every other, whether it is leaf spine, except for a few extra configurations, right? And we talked about slow convergence also. So if you see the class topology ensures it is ECMP. So does slow convergence is actually an issue? And do you really need a new protocol which need to be implemented for this?
Yes, slow convergence can result into black holing in some cases that we discussed in the class with the pod topology. If your convergence is very, very slow, then it can result into black holing because you don't have a certain link, but you're still doing ECMP, right? I mean, you're not converged, so you still don't know you're going to reach there, right?
You have mechanisms, you have BFD, right? So when you say ECMP, it happens at the hardware, right?
Well, so this is path ECMP, not link ECMP. Okay, so this is the two components of the ECMP may have intermediary nodes. Yeah, so BFD running on a link, that would be great. That would tell you one link's down, put all the traffic on the other link. But when you've got diverse paths to a destination, the BFD wouldn't scale because you'd have to run BFD to every possible destination.
Thank you.
Talks about management ports and then flood over those management ports. Those management ports are connected, on a LAN, and then you are using DRBDR kind of flooding optimizations to flood on inside the DCs. And then your actual traffic forwarding will happen on your other P2P links, but your the topology flooding, the topology flooding is completely blocked on those links where traffic is forwarded. It only happens on the management ports. So that's another idea. So we have this LSBR. This is another working group, and then this is trying to solve the problem in BGP itself. So we have the problem of slow convergence. We have the problem of additional configurations, and we have the problem of black holing in BGP, as we saw in BGP inside data centers, and this is trying to solve this is trying to solve that using, they have the new NLRI which is very similar to BGP LS and NLRI, so it advertises nodes and links, and then BGP itself natively computes the SPF using that topology information, and then instead of using BGP best path selection, it uses the computed information to program the routes. So there is a lot of interest in this one as well, and there is a separate working group working on this for standardization. So basically, what I want to summarize is there are a lot of new mechanisms being proposed to solve in DCs. As I'm talking about all these techniques, I think I guess all of you would have chosen, your favorite. You think, oh, I think this is going to work. We really don't know which one is going to work, and I'm pretty sure everyone has chosen their own, and all are different. Different mechanisms that, you guys think that that's going to. So at this stage, it's still not very clear which one is going to sustain. So I want to leave with that thought, and if that gives you some, gets your brain cells tickling, and then that's what is the objective of this talk.
Okay. So I am Annapurni. So I have a question. Like we say, as part of the data center requirements, we want data center want to avoid like Cisco's and Junipers because you are really expensive, right? So we come up with something which is already available in the market. So if you see, like that's why if you see in the large data center, we go for eBGP, correct? And if you see the configurations is more or less similar on every other, whether it is leaf spine, except for a few extra configurations, right? And we talked about slow convergence also. So if you see, the class topology ensures it is ECMP. So does slow convergence is actually an issue? And do you really need a new protocol which need to be implemented for this?
Yes, slow convergence can result into black holing in some cases that we discussed in the class with the pod topology. If your convergence is very, very slow, then it can result into black holing because you don't have a certain link, but you're still doing ECMP, right? I mean, you're not converged, so you still don't know you're going to reach there, right?
You have mechanisms, you have BFD, right? So when you say ECMP, it happens at the hardware, right?
Well, so this is path ECMP, not link ECMP. Okay, so this is the two components of the ECMP may have intermediary nodes. Yeah, so BFD running on a link, that would be great. That would tell you one link's down, put all the traffic on the other link. But when you've got diverse paths to a destination, the BFD wouldn't scale because you'd have to run BFD to every possible destination.